Hi everyone, welcome back to Z Physics. Today we're going to be doing some question practice on potential dividers. In order to make the best use out of this video, please have a look in the description and you're going to find some links to the actual past paper questions. If you attempt those independently first off, this will be ideal. Then you can check your answers with my solutions. Also, please note that these are not official solutions and these are just my solutions. Okay, well, let's get started with the first question. So let's have a look at this question. Figure 3.1 shows how the resistance of the thermistor varies with temperature. We can clearly see that the resistance is decreasing with temperature. So we have the thermistor is placed in this potential divider circuit, and A is asking us to state and explain how the current in the circuit changes as the thermistor is heated. The first thing that we need to write down is that the resistance of the thermistor will be decreasing as the temperature is increasing. Now, because of that, the total resistance in the circuit will decrease. So I'm going to write this down. The total resistance in the circuit decreases. Because the total resistance decreases, and remember, the current I in the circuit is equal to V over R, the supply voltage, the EMF remains constant. So I'm going to say that the EMF V is constant, but R is decreasing. Therefore, the current is increasing. So, part B, use figure 3.1 to calculate the voltmeter reading when the temperature of the oven is 240 degrees C. We can see that, no pun intended, that at 240 degrees Celsius, then the resistance is going to be 40 ohms. So that's two lines, yeah, each of them is 20. So I'm going to write down over here that at 240 degrees C, the resistance of the thermistor is equal to 40 ohms. So in a nutshell, we know that the resistance across here is 40 ohms. Now, to calculate the voltmeter reading, we're going to need the current in the circuit, and because those two resistors are connected in series, or those two components are connected in series, we know that our total is going to be equal to 240 ohms. Using that, we can calculate the current in the circuit simply by V over R. So it's going to be 6.0 divided by 240. That's going to give us 0.025 amps. Okay, so now that we know the current that is going all the way through this circuit, we could calculate the voltmeter reading just using V is equal to IR as applied to this thermistor over here. So we know the current is 0.025 multiplied by 200, and that's going to be equal to 5 volts. So part C, a light-dependent resistor is another component used in sensing circuits. Complete figure 3.3 with an LDR between X and Y. And look at that, I've already done this. So I've included a little LDR. So remember, that's just the standard resistor symbol with some arrows which are falling on top. The circle is generally not required. Okay, state within a reason how the voltmeter reading varies as the intensity of the light incident on the LDR increases. Well, the LDR has a very similar curve for its resistance against light intensity. So as the light intensity increases, the resistance of the LDR will be decreasing. Now, because of that, I've written over here that the resistance in the circuit decreases. This means that it's the total resistance. Because of that, the current will be increasing, so we can write this down. So the current in the circuit will increase. The current in the circuit will increase. Because the current in the circuit increases and the voltmeter is across the fixed resistor, the value of V here is equal to IR, and R is fixed, it cannot be changed. Therefore, if I increases, V should increase. So we're going to say that the reading increases as V is equal to IR, I increases, and R is fixed. Okay, well, let's have a look at this one. Figure 3.1 shows a thermistor and a fixed resistor of 200 ohms. They're connected through a switch, and we have an EMF of 24 volts. The voltmeter across the fixed resistor has a very high resistance. Okay, so this tells us that we can think of this as a series circuit essentially. And when the switch S is closed, the voltmeter initially reads 8 volts. So the reading here is initially 8.0 volts. Calculate the current in the circuit. Well, across this fixed resistor, the resistance is 200 and the voltage is 8. So this means that we can apply Ohm's law directly. Ohm's law says that V is equal to IR, rearranged of course for I. Let's write this over here. We get that I is equal to V divided by R, which is going to be equal to 8.0 divided by 200, which leads us to a current of 0.04 amps. The next part is asking us for the potential difference across the thermistor. Well, if we have 24 volts across here and 8 volts across here, this means that we'll have 16 volts left over for the thermistor. So we can write this directly down as 16 volts. To calculate the resistance of the thermistor, all we really need to do is once again just use V is equal to IR. Rearranging that for R, we are going to get that R is V over I, and the voltage across the thermistor is 16 volts. The current, because this is a series circuit, the current will be the same everywhere, so it's going to be 0.04 as we've calculated like so, and that leads us to a value for the resistance of 400 ohms. For the next part, part 4, we need to calculate the power that's been dissipated in the thermistor. Well, we know the current through the thermistor, we also know the voltage, we know its resistance, so we could use multiple methods to do that. So for instance, what I could use is that power is VI, and we know that V is equal to IR, so this means that the power will be equal to I squared multiplied by R. This is a formula that's actually given in your formula booklet as well. Now the current is 0.04 squared multiplied by the resistance, which is 400. Plugging this into a scientific calculator, we are going to get 0.64 watts. So a few minutes after closing the switch, the voltmeter reading has risen to a steady value of 12 volts. Now this means that this voltage here is no longer going to be 8, but it will be increasing up to 12 volts. Well, remember, if this guy here has increased up to 12 volts, in fact, should we just change that completely? So if this one here has moved to 12 volts, then this one here would be down to 12 volts as well. Now explain, how could that have happened? Well, after the circuit has been running and this switch has been closed, the temperature of the thermistor would have increased. So this will be our first mark over here, and I'm going to bullet point it, and I'm going to write that the temperature of the thermistor has increased. Now, what happens when the temperature increases? Remember, the graph for resistance against temperature for a thermistor looks like this. So this means that as T increases, the resistance decreases. So this would mean that the resistance of the thermistor, so the resistance of the thermistor has decreased. Now, because the resistance of this thermistor has gone down, this means that the overall resistance in the circuit has decreased, therefore the current in the circuit increases. This is really important. I'm just going to highlight that over here. So the current in the circuit increases. Now, because the current in the circuit increases, remember V is equal to IR across this fixed resistor. So if R is fixed, it doesn't change, and I goes up, then this means that V is going to go up as well. Therefore, the PD across the fixed resistor increases. Should just write resistor here just to be absolutely sure. Okay, perfect. Let's go on to the next one. Okay guys, so next one, explain why the resistance of the thermistor must be 200 ohms. Well, it has exactly the same PD as the fixed resistor. Remember, it was 8 before, however, this one here dropped to 12, which means that this here must have increased to 12 by Kirchhoff's second law. And if they have the same PD and the same current, the resistances must be equal. In other words, because R is equal to V over I, if V is the same and if I is the same, this means that R will have to be the same. Okay, the next one is really interesting. On the graph below, what we need to do is sketch the possible IV characteristics for the fixed resistor. Label this R. Please don't forget to label any graphs and loose marks like this. So notice that this is a straight line. Because we're given some numbers, it's not going to be a pure sketch, but we'll also need to add in some numbers. When the resistance is 12, sorry, when the voltage, the PD across the fixed resistor is 12, we can calculate the current at that by dividing it by 200. In fact, let me just do that real quick over here. So 12 over 200 will be 0.06 amps. So this is where the number 0.06 comes. And the straight line of the fixed resistor will pass at that point. Additionally, for the graph, which has been labeled with T for thermistor, this will also pass through the same point because this guy here also has 200 ohms. So this means that essentially the IV characteristics of the thermistor will pass at exactly the same point with a current of 0.06 amps at 12 volts. Additionally, it will also pass through this point, which is 8 and 0.04. However, with a straight line gradient, this is kind of inevitable. The IV characteristics for a thermistor, remember it's an upwards trending curve. So one mark will be for that and another mark is going to go through that correct passing through that point. Okay, folks, hopefully this question makes sense. On to the next one. Okay guys, next we'll be looking at question 4 from June 2010. So we have this graph of how the resistance of a light dependent resistor LDR varies with the intensity of light incident on it. State how the resistance of the LDR changes with light intensity. And this is quite an easy mark, so we can clearly see that the resistance is decreasing. So we're just going to write this down. The resistance is decreasing. As light intensity increases. Okay, question B. So figure 4.2 shows a light sensing potential divider circuit where the LDR is connected in parallel to a voltmeter and a data logger. So the battery has an EMF of 9 volts and no internal resistance. The 1.2K resistor is made of carbon. The potential difference across the LDR is 6 volts. Okay, so from here to there we have 6 volts. Calculate the potential difference across the 1.2 kilo ohm resistor. So we have 6 across here, 9 across there. By Kirchhoff's second law, that the sum of the EMFs, in this case that's 9, has got to equal to the sum of the PDs, which is here plus there. This means that over here we need to have 3 volts. Okay, well, let's have a look at part 2. Calculate the resistance R of the LDR. Well, in order to do so, we're going to need the current in the circuit because we don't know the current just yet. But we can figure it out pretty easily. So looking at this portion of the circuit, we know the resistance, we also know the potential difference. So the current in the circuit, let's call that I, will be equal to the PD across the fixed resistor divided by its resistance R. I'm going to write it for R fixed. Okay, so the PD is 3 volts and our resistance is 1.2 kilo ohm, so that's 1200 or 1.2 times 10 to a power of 3. For to divide those, we're going to get 2.5 times 10 to a power of minus 3 amps. Now, once we have the current in the circuit, because we have the potential difference across the LDR, this means that we can very easily calculate the resistance across the LDR. So R will of course be just equal to the potential difference V divided by the current in the circuit. So this is going to be 6 divided by 2.5 times 10 to a power of minus 3. And if we put that into a scientific calculator, we're going to get 2,400 ohms. Now let's just be careful though, because they're asking us for the answer in kilo ohm, so this is going to be 2.4 kilo ohms. Okay guys, well, next part, use figure 4.1 to determine the light intensity when the PD across the LDR is 6 volts. Now remember, this actually ties in with the previous question. This is because 6 volts was essentially the voltage for which we calculated the resistance of the LDR. So we know that at 6 volts the resistance is 2.4 kilo ohms. So we can use that directly to determine the light intensity. So we can see that when the resistance is 2.4, the light intensity is right there in the middle between 40 and 60, so it's going to be 50 watts per meter squared. So we can write this down. So this will be 50 watts per meter squared. Okay, next one. Figure 4.1 shows the change in resistance when the light intensity rises from 60 to 80 is half a kilo ohm. State the change in resistance when the light intensity rises from 20 to 40. Okay, well, because the gradient of the tangent here is going to change, also the amount is going to change. So if we're going from 20 to 40, we're going to be going from here to here. So this is way more than half a kilo ohm. So we are going from 5 to about 2.8, which is just here. So it's going to be 2.2. So from here to here, it is 2.2 kilo ohms. And that's going to be the answer to this question. Okay, next one here, larger changes in data log the data log voltage observed for changes at low light intensity rather than in high intensity. Explain this. Okay, well, this is relatively straightforward. First off, we notice that the changes in resistance is larger for smaller light intensities. In fact, they've actually spelled this out for us in the question, which is incredibly useful. Here we know that when we go from 60 to 80, the difference is about half a kilo ohm, whereas if we go from 20 to 40, we found out it was 2.2. We know that this is true because this graph here is much steeper here compared to there. The gradient of the tangent of this graph is much larger. So overall, this means that the change in resistance is larger for smaller light intensities. The next part would be to see how this corresponds to output voltage. We know that the formula for V out is R2 over R1 plus R2 times your input voltage. However, this is, by the way, given in your formula sheet. Rather than R1, I've written here 1200, which is the value of our fixed resistor. So if the change in R2 is larger, there will be a corresponding change, larger change in the output voltage. Part D is really interesting. It's a standard potential divider question, really important one. So when the circuit of figure 4.2 is operated for a long time, the carbon resistor becomes hot. The resistivity of carbon falls as the temperature rises. State and explain the effect on the potential difference across the LDR. So the important bit is to take things logical in this case. So we know that because the resistivity of carbon falls, this means that the total resistance in the circuit will decrease. If the resistance in the circuit decreases, this means that the current must increase. And if the current increases, well, this means that the PD across the LDR must increase. The reason for that is because as V is equal to I times R, if this guy R of the LDR remains the same but I increases, V will have to increase. Okay guys, hopefully you found this video useful. If you have, please give it a thumbs up, and thank you very much for watching, and I will see you in the next video.